We just introduced several algorithms to generate permutations. Actually, the programming environments nowadays also provide us a lot of useful tools. For example, in Java here, permutation functions and combination functions. Some other algorithm tests are also introduced how to generate permutations. Also, in the academic world, we will find a lot of papers on how to generate a permutation effectively in different situations. Actually, what we use the most is two useful tools provided in STL. Let's see, in STL, there are two functions. One is next permutation, another is pre-permutation. Actually, these two functions will generate the next permutation in lexicographic order. So, let's see that if we use these two functions to generate permutation, what will happen? Here, we wrote a very simple piece of code to show the usage of next permutation in STL. Of course, pre-permutation is similar. The basic idea is to give an original string and then we call next permutation in a loop to generate all permutations. Let's run it. For example, let's generate all permutation of A, B, C, D. The results are generated soon. What about process a larger string? For example, A, B, C, D, E, F, G, H, I, J, which has 10 characters. Let's see how long would it take. The screen is keeping flashing. 2 minutes passed. We will see that only for 10 character strings, it needs to nearly generate 10 factorial permutations. Even if we use the next permutation functions provided in STL to calculate, we still need a lot of time. So we will see that for generating permutations, the sizes of problems are increasingly very rapidly. If we want to process all permutation of 10 character strings, there is no effective solutions. After watching the demonstration, we might think, oh, that is n factorial extremely large. Yes, it is. So how large is this n factorial? Let's take a look at this number. As we know that n factorial is keeping multiplying numbers, so it could cause stack overflow quickly. So we need to find an effective method to estimate it directly. There is a formula called Stirling approximation. The significance of this formula is that it doesn't multiply to calculate n factorial. Rather, it uses an approximation method to calculate n factorial approximately. How should we demonstrate it? We could read the reference materials. Now let's give the result. For n factorial, when n is approaching unlimited, it's approximately equal to this number. So let's calculate how large could n factorial be. This is a table for it. For example, when n is equal to 60, with Stirling's formula, we find that 60 factorial equal to this one. How large is this number? If we want to generate all permutation of 60 numbers, and if the speed of computer is to generate 10 to the 7th permutations per second, how long would it take? Let's calculate. The answer is surprising. It will need 2.65 times 10 to the 67th power years to list all permutation of 60 numbers. So factorial is increasing extremely rapidly. This means that we need to have better method to deal with specific problems. So far, there have been a lot of algorithms to generate permutation. There are at least more than 20 algorithms could generate permutations. Of course, this is not all. Hopefully, you could do some research to see whether to discover some faster and better algorithm to generate.